SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 23, and today we are going to discuss a very interesting topic that is about bending of beams. Okay. So, in your first year mechanics course, you may have come across beams subjected to shear force and bending moment. Now, you may have seen this beam which was subjected to distributed load and this need not be vertically downward, it can be vertically upward also or it could be tilted also. Basically, the force is distributed over the surface, and then you may have seen that there is a terminal moment also, or there could be a couple somewhere in the middle also. Okay. And you would have drawn what is called the shear force diagram or the bending moment diagram. But we just stopped there in the first year. Here we are going to see how does the beam deform when it is subjected to distributed load or terminal bending moment or couple. Okay. So, this course is about deformation, right. So, we want to see how does a beam deform, and we start with the simplest case of bending of beams. And let us suppose that the beam is a rectangular beam to begin with, and it is subjected to just terminal moment. Okay. So, let me draw that picture. So, think of a beam which is rectangular all right, and it is subjected to terminal couple. Okay. Let us define the coordinate system here. So, suppose x axis is along the axis of the beam, y axis goes vertically upward and z axis is coming out of the paper. Okay. So, in this case you see we have two end cross sections. So, over the right cross section here, the moment that we are applying is along the z axis. Okay. So, we can call this as m z, and it is acting in the positive z direction. So, this is the positive x plane, and on the positive plane the moment is acting in the positive z direction. Okay. Whereas, on the left side, which is the negative x plane, its normal is negative x. So, on that the moment is acting in the negative z direction. Okay. So, this is minus m z, and therefore, the total moment on the system is 0, and so it is going to be in static equilibrium, right. But we want to see when we apply this moment to this system, how is the beam going to deform. Okay. So, think of a rectangular beam and we hold the two ends and apply moment. Okay. So, when you do that experiment, you will see that the beam gets curved, and we want to analyze that deformation, that is called the bending of beams. All right. You can cut a section anywhere. Suppose I cut a section somewhere in the middle, so on this cross section also the moment that is acting is still mz only. So, on any cross section you cut, we have the same moment acting. You can get this just by drawing the free body diagram of one half of the beam and then show that the moment in the internal cross section is same as what you applied, and it is the same throughout. So, this is also called pure bending. Okay. So, we also call it pure bending of beams. So, moment is same throughout. And the moment that is acting here, that is called bending moment. It is not along the axis of the beam, the moment is about the z axis, right. It is not about the x axis. If it were about the x axis, then it becomes torque, and torque induces what is called torsion, which we learnt in the last few lectures, but now we are doing bending. So, when the moment is perpendicular to the axis of the beam, it induces bending in the beam gets curved. So, therefore, such moments are called bending moment. Okay. And the simplest situation is when the bending moment is same all along the cross section, and we call it pure bending. When you cut the cross section, we only see bending moment, we do not see any force. Okay. So, there is no force in the cross section. All right. So, it turns out when we do this, the beam actually deforms into a circle. It takes the shape of a circle. Okay. So, let me draw that circle. So, here is that circle. As the beam deforms, the top line, for example, this is getting compressed. Just try to visualize this. As you deform the beam, the top surface gets compressed, whereas the bottom surface is getting stretched. So, the bottom surface that is getting stretched. So, you can actually think of any line along the axis of the beam on the bottom surface, and due to this deformation that line is getting stretched, right, whereas any line along the axis on the top surface that is getting compressed. So, you see as you go from bottom to the top, the deformation is changing from being stretched to being compressed. So, there has to be somewhere a line which will neither get stretched nor compressed, right, because this has to change in a continuous fashion, right. So, there will be a line which will neither get stretched nor get compressed, and that line is called neutral line, because it is neutral to bending. Okay. So, we can draw that. So, we call this neutral line. Because it is neutral to the deformation, it is not able to see that the beam is getting deformed. Okay. And if I draw its 3D picture, all right. What we see here is just a neutral line, but we can also think of a neutral plane. So, any axial line on this neutral plane is not getting stretched or compressed. Okay, so, none of these axial lines are getting stretched or compressed. So, therefore, it is the whole family of lines which form a plane, and we call it neutral plane. So, this plane is called neutral plane. Because none of the lines along the axis on this plane is getting stretched or compressed. All right. Now, let us try to see how much is the elongation or compression on these axial lines, okay, which we can also call as fibers, axial fibers, longitudinal fibers, because they are along the axis of the beam. So, we can call them as longitudinal fibers also. Okay, so, that is the 3D picture. Let us do a 2D picture to simplify the analysis. So, we have this beam which is bent into a circle. It is just the front face of the beam, and fix an axis here. So, this is your x axis, then that is your y axis, and what comes out is the z axis, and the moment is along the z axis. Okay. And as the beam gets bent into a circle, there will be a center to this circle, right. So, that circle has its center somewhere over here, okay. And let us take a longitudinal line which is at a distance y above from the neutral line. Okay. So, we have this neutral line also here, and we do not know where exactly it is. It has to be somewhere in between the top and bottom surface. So, that is the neutral line. But then any arbitrary longitudinal line denoted by this green line here, we want to know how much is the stretch in that line. So, we say that this is at a distance y above from the neutral line. All right. Now, you see all these lines, the blue line or the black line or the dashed green line, they are all part of the circle, right. They all form different circles. The blue line will say that the circle has got the radius big R. Okay. From the center to this arc, the radius is big R. For the green line, which is not a neutral line, the circle would then be big R minus y, is not it? Because the green line and the blue line are separated by y. So, for the green line, the radius is big R minus y, correct. Let us suppose this angle here, that is theta, right. So, what can you say about the length of each of those lines? So, for the neutral line, the length for the neutral line, which we denote by n, so that is equal to the radius r into theta, right. And since this line is neither getting stretched nor compressed, this should be same as the original length, which we will say is big L. Okay. So, the length of the beam originally is big L. After deformation, the neutral line still will have the same length. What can we say about the green line? What is the length of the green line? Okay. So, for green line, the length of the green line, that is the radius big R minus y times again the same theta, is not it? But we could also write this as big R minus y into big R times theta divided by big R, and then we say that big R times theta is actually the original length, which is big L, and then divide by big R, right. So, that is the final length of the green line. So, how much will be the longitudinal strain in the green line? So, the longitudinal strain epsilon for the green line, how much is that going to be? That is the final length minus the original length, which is big L. So, for all the longitudinal lines here, the initial length is big L, right, because it was a rectangular beam, and we divide by big L. What we get here is simply big R minus y over R into L minus L divided by L, which is equal to 1 minus y by R into L minus L divided by L, and that is simply minus y over R. So, this way we are able to find out the longitudinal strain for any axial lines at a distance y from the neutral line. Remember that the location of the neutral line is still unknown. So, I can write here that the location of the neutral line is still an unknown. Okay. All right. So, this epsilon g, which is the longitudinal strain, it is actually also epsilon x x, right, because the lines were originally along the x axis. So, it is epsilon x x. So, this is same as epsilon x x. Now, let me draw the cross section of the beam. So, it was a rectangular beam. So, the cross section is going to be a rectangle, and then we have this neutral axis. You see, in the cross section, the neutral plane, when it cuts the cross section, we get a line and we call it neutral axis. So, this is your neutral axis. So, this is the line that the neutral plane and the cross section both contain. So, it is common to both of them. And then we had any green line here which was at a distance y from the neutral axis, and remember that we also had the coordinate system. So, this is the origin and y axis is going vertically upward, whereas the z axis is to the left and x axis is now coming out of the paper. So, this is cross section. Okay. So, therefore, x axis is now coming out of the paper. So, what can we say about epsilon x x at any point in the cross section? So, think of any point here y comma z in the cross section. So, epsilon x x in the cross section, as we have found out, is minus y by r. So, it is dependent on y, but independent of z. So, we take any line with a constant y, for example, this green line. So, any point on this green line has got same epsilon x x, because it is independent of z. Okay. Okay. Now, what can we say about sigma x x then? So, let us try to use stress strain relationship. We know that epsilon x x is equal to 1 over E into sigma x x minus nu times sigma y y plus sigma z z. So, that is the relationship for isotropic materials. Okay. So, we want to find out what is sigma x x. Now, look at the beam again. We said that this is the case of pure bending. So, we are only applying moment at the two end cross sections, and we are not doing anything on the lateral surface, on the top surface or the bottom surface or the front surface or back surface. On each of those four surfaces, we are not applying anything. So, as the beam bends, those surfaces are allowed to relax freely. So, in the y direction or in the z direction, it is free to relax, there is no constraint. So, can we say that sigma y y and sigma z z is then 0? That is a nice approximation, right, because we are not applying anything on the surface. You see the top surface is the y plane. So, the traction on y plane is 0, right, because we are not applying anything. So, traction on y plane is 0. And what are the various components of traction on y plane? So, if you recall, we have tau on y plane. So, it is tau x y, sigma y y and tau z y, right. So, on the top surface, none of these three components are there. So, sigma y y is 0, and since it is allowed to relax freely, we can also say that even any point within the beam, sigma y y is 0. So, that is an approximation. You see, to be rigorous, sigma y y is 0 only on the top surface, but we are approximating here that it is 0 even within the beam. So, at any point in the cross section sigma y y is 0. So, it is an approximation. Likewise, sigma z z is also 0 at any point in the beam. And why do we do this approximation? Is because the beam is allowed to relax freely. So, if you allow me to use that approximation, then we can come back to this equation and say that sigma y y is 0 and sigma z z is 0. So, it is an approximation. So, this means sigma x x is then E times epsilon x x, and then this becomes minus E into y over r. So, that is our sigma x x. If we try to draw its variation, so here is the cross section, and we have this neutral axis and this is your y axis. On the top side of the neutral axis, sigma x x is compressive, whereas on the bottom side sigma x x is tensile. So, if we draw the variation, then this is how sigma x x is going to vary. Okay. So, this is the compressive side, whereas this is the tensile side. Okay. So, remember again sigma x x is the normal component of traction on the cross section. And we said in the beginning that it is a pure bending case. So, in the cross section, when you cut a cross section, then the cross section has got only bending moment. There is no net force in the cross section. It has only got a bending moment. All right. So, what does that mean? If you integrate sigma x x in the entire cross section, it should be 0, right, because the integration of sigma x x over the whole cross section, that gives you the force in the cross section along the normal to the cross section, right. And since the total force is 0, this integration must be 0. Okay. So, we can now say that the integration of sigma x x over the entire cross section that is equal to 0, and this is because no force acts on the cross section right. But let us see what is the fallout of this observation. So, this implies integration over omega naught minus of the Young's modulus E times y by r dA is equal to 0. So, I took the Young's modulus outside, assuming that the whole cross section is of the same material. If the material were different, then we will have to divide this integration into various domains. For each of the material we will have one domain, and Young's modulus will then be constant in that particular domain. Okay. But for now, for simpler analysis, we say that it is the same material. So, I simply take out the Young's modulus out of the cross sectional integral, and you see we also have this big R, that is also called the radius of curvature. Okay. So, big R, we also call it the radius of curvature. Which is also the radius of neutral line, correct. Okay, so that is the radius of curvature r, because it is for a neutral line. So, it is also a constant, although we are looking at different points in the cross section, but this big R is for the neutral line. So, it also comes out of the integral, and then we have minus E by R integration over omega naught y dA is equal to 0. Okay. So, it says that the neutral axis has to be at such a location such that when we measure y from the neutral axis, the first moment of y is 0. And what is the first moment? The first moment actually gives us the centroid, is not it? The first moment gives us the location of centroid for any area. So, what we figure out from here is that the neutral axis must pass through the centroid of the cross section, then only the location of the centroid would be 0, right, because this is equal to y bar, the location of the centroid, into area of the cross section, which is 0. That means y bar is 0. Okay, so, what this tells us is that the neutral axis must pass through the centroid of the cross section. Okay. So, we got at least one unknown worked out, the location of the neutral axis. We still have another unknown, that is the radius of curvature. So, the radius of curvature is still an unknown. Okay. So, to find that, maybe we should find out what is the total moment that is acting on the cross section, right. Let us again draw the cross section. And here we are working with a rectangular cross section, and having known that the neutral axis has to pass through the centroid, which in this case would be at the center of the rectangle, right. So, the neutral axis will exactly divide this cross section into two parts. Okay. And this is the x plane, right, it is a cross section. So, it is an x plane, and at any point which is y comma z will have traction acting on this plane, and let us try to find out moment due to this traction about the center of the cross section. Okay. So, here is the center. So, we can also draw the axis. So, that is your y axis, and then this is your z axis. Okay. So, what is the moment about the origin of the cross section? So, that is the integration over the cross section, and then the arm, any point in the cross section has got its position vector y j plus z k. So, that is the arm cross with the small force, right. So, that is the traction on x plane times d a. So, when we do this integration, we get the total moment about the origin of the cross section. So, let us work this out. So, this is equal to integration over the cross section y j plus z k cross product T x. So, it has got 3 components, sigma x x into I plus tau y x into j plus tau z x into k times d a. Okay. And we have already found out what is sigma x x in this case, right. And you see we have 2 other things here, tau y x and tau z x. So, these are the shear component of traction that would be acting in the cross section. In general, we will have shear also in the cross section, but the resultant of shear traction, that has to be 0, right, because the total force is 0. Anyway, so this is the moment about the origin. What can we say about the moment about the z axis, because that is something which we have prescribed, right. So, the question mark is, what about m z? So, that is simply moment about the origin dotted with k, right. So, that is your m z. So, what is that going to be? So, we have this integration again, y j plus z k cross product sigma x x I plus tau y x j plus tau z x k, and then the whole thing has to be dotted with k, and then we have d a, right. And we know that whenever we do cross product of 2 vectors, what we get is perpendicular to the 2 vectors, and here we have to dot with k. So, none of the 2 vectors that we are doing the cross product should be along k, is not it? If any of the vector is along k, then cross product will give me something perpendicular to k, but then we have to dot with k. So, it will give me 0. You see, for example, look at this combination. So, what is that going to give me? K cross I is j. So, that gives me z times sigma x x into j, and then we dot with k. So, this is 0, right. So, therefore, we can discard the components here which are along k, because they will not participate in m z. So, with that observation, let us forget about these 2 components. So, now we can write this as integration over omega naught of y j cross product sigma x x I plus tau y x j, and then dot with k d a, but again j cross j is 0. So, that does not contribute, and we have only the j cross I, which is minus k, right. So, what we get from here is integration over omega naught of y into sigma x x times minus k dot with k d a, okay, which is again minus integration over omega naught y times sigma x x d a, all right. and now we can plug in the formula for sigma xx, which we have just figured out. So, look at this formula. So, when we plug it back in the final equation that we have, the minus minus cancel each other and we get integration over omega naught of E by r into y square dA. Okay. And this has got a name, this integral y square dA, that is the second moment of area about the z axis. Okay. So, that is the second moment about z axis. So, we call it I z z. So, this number here, that is I z z. Okay. So, what we have finally found out is that m z, which we have prescribed, should be equal to E times I z z times 1 over r. You see, the Young's modulus is the property of the material, I z z is the property of the cross section, because it is an integration over the cross section. So, it is a geometric property. So, we can write here E is the material property and I z z is the geometric property of the cross section. So, depending on what moment we have applied at the two ends of the beam, the radius of curvature that gets generated is then given by this formula. Okay. So, this simply tells us that the radius of curvature big R is equal to E I z z over the bending moment m z. Okay. And 1 over r is also called curvature. Big R is the radius of curvature, but its inverse, that is called curvature. All right. So, we will denote this 1 over r as curvature, and let us use the symbol kappa for it. Just as we have used kappa for twist earlier, now we are going to use kappa for curvature. Okay. So, this tells us also that the curvature kappa is moment m z divided by E I z z, okay, or m z is equal to E I z z times the curvature, bending curvature. Okay. So, we call it bending curvature. And this combination here, that is called bending modulus. So, bending modulus of a beam is the combination of material property as well as the geometric property. If we have got a beam and we apply some moment, then the curvature that gets induced in the beam depends on what is the bending modulus. If the bending modulus is very high, then the curvature induced would be small. So, it would be difficult to curve a beam, right. So, we can make this remark here. So, large curvature means beam is quite curved, right. That is because the radius is small, whereas small curvature, this implies beam is almost straight, and that is because the radius is large here. We can also look at it from the picture. Suppose we have this beam, in one case it gets curved like this, and in the other case let us say it is almost a straight line. So, in the first case, since it is very much curved, the radius will be small, right. So, its radius would be somewhere over here, whereas in the second case the radius would be quite large. And if it is flat, then the radius is infinity. Okay. So, here the radius r is large and therefore, curvature is small. And this relationship that the moment applied is equal to E I z z times curvature simply tells us if the beam is very much stiff in bending, that means if the bending modulus is large, then it is very difficult to curve a beam. Now, with this formula we can also find out what is sigma x x. Recall that sigma x x was minus E times y into curvature, right. It is 1 by r, but then this becomes minus E times y into curvature, and then this is minus E y into m z over E times I z z. So, this implies again that sigma x x equals minus m z into y over I z z. Okay, so, we have two formulas for sigma x x. You either use this or you say it is minus E into y by r. All right. Let us try to find out what is I z z for rectangular cross section. Okay. So, for a rectangular cross section, suppose that this is the height h and that is the width b, and here we have the neutral axis, and we have to find out the integration of y square dA. So, in this case you can see that any point on this line they have the same y, is not it? So, we could also write this as integration over y square, and dA is dy dz, correct. The integrand, you see, it is only a function of y, it is not a function of z. So, we can simply carry out the z integral. So, this becomes integral y square dy, and this goes from minus h by 2 to h by 2, and we have the z integral dz going from minus b by 2 to b by 2, right. So, the z integral is a constant, and this gives us b. So, what we have is b times integral y square dy minus h by 2 to h by 2, and this then becomes b over 3 y cube minus h by 2 to h by 2, and that is again b over 3 into 2 into h by 2 to the power whole cube, right, and that is finally 1 by 12 b h cube. So, that is your I z z for a rectangular cross section. So, can you see that if you increase your h, then IZZ is increasing, right, and if you increase your b, then also of course IZZ is increasing, but with h it is more sensitive because it is h to the power cube. So, a small increase in h brings about large increase in IZZ. So, if you take two beams having same Young's modulus and think of first beam with a smaller h and second beam with larger h, then the second beam will have larger bending modulus, right, because IZZ for the second beam is large. Although the Young's modulus is the same, the IZZ for the second beam is large. So, it is difficult to bend the second beam then, correct, because its bending modulus is larger, all right. So, that is for the rectangular cross section. We can also work it out for other cross sections. We simply have to find out the IZZ for that particular cross section. Let us also try to see what really happens to the cross section. Does the shape of the cross section change when we bend a beam? Initially it is rectangular, so after deformation what happens to the shape of the cross section? And now let us again recall that we have y axis and z axis here. So, we have found out epsilon x x, that is minus y by r. What can you say about epsilon y y and epsilon z z? So, epsilon y y, we know it is equal to 1 over e into sigma y y minus nu times sigma x x plus sigma z z. But then we said that sigma y y and sigma z z are almost 0. So, this implies it becomes minus nu over e into sigma x x, which is also minus nu times epsilon x x, right. So, this becomes nu into y by r, correct. Likewise, we can also show that epsilon z z is equal to epsilon y y and equal to nu times y by r. Now, think of a line in the cross section along the y axis. So, let us think of this green line for example. How much would be the change in length of this green line? So, we have to find out what is the normal strain along this green line, epsilon y y, and you see that epsilon y y is nu times y over r. So, on the top side of the neutral axis, epsilon y y becomes positive, and on the bottom side epsilon y y becomes negative. So, one half of the green line will see positive normal strain, whereas the other half is going to see negative normal strain. So, as a whole the length of the green line will not change then, right. So, this implies length of the green line as a whole does not change. Okay. What can we think about a line which is along z axis? Let us think about that. So, think of a blue line here. So, if you want to know the change in length of the blue line which is along the z axis, we have to think of epsilon z z, right. So, now epsilon z z, which is equal to epsilon y y, is also nu times y over r. But you see, for the blue line, every point of the blue line has got the same y coordinate. So, that means every point of the blue line will have the same epsilon z z, nu into y by r. And again, on the top side of the neutral axis, the blue lines will see positive longitudinal strain, whereas on the bottom side the blue lines will see negative longitudinal strain, which means on the top side the blue lines are going to increase and on the bottom side the blue lines are going to decrease, and you see that the strain is proportional to y. So, that increase or decrease happens in a linear fashion. So, we can now visualize what happens to the rectangular cross section, is not it. So, if we have a rectangular cross section to begin with, then it is going to change and it becomes a trapezoid. Here is the neutral axis. That is because on the top side of the neutral axis the lines are getting stretched and on the bottom side they are getting compressed. So, you see a rectangular cross section becomes a trapezoid. Another interesting thing to see here is, let us think of this z line again. So, here is the z line. So, can you see what is the angle here? This angle has become more than 90 degree, right. So, this angle which was initially perpendicular, you see it is initially perpendicular, it has now become more than 90 degrees. So, there is a change in angle between these two lines. Now, what are these two lines? So, this is along y axis and this is along z axis. So, whenever there is change in angle, it induces shear. So, this tells us that gamma y z is less than 0, right, because the angle has increased. So, gamma y z becomes negative, but if there is gamma y z, then this also implies we will have tau y z too, right, because for a isotropic material shear stress is proportional to shear strain. So, tau y z is then also less than 0. So, it is not equal to 0, that is something to look at. But then concentrate on a point here, which is on the surface, okay, at the periphery of the cross section, and it is on the free surface. Now, see what surface is that? So, this surface is actually Z surface, is not it? So, the beam goes into the paper and the surface is then the Z surface, its normal is E z or E 3 and it is a free surface, is not it. When we are bending the beam, we are only applying moment on the end cross sections which were the x plane, but the lateral surfaces were free. So, the Z surface is also free, that means all the traction components on the Z surface has to be 0. So, it is a free surface, which implies all traction components on Z plane will be 0. Which means that tau x z, tau y z and sigma z z, they are all 0, but let us concentrate on tau y z, which is 0. But from here you see that we are finding out tau y z not equal to 0. So, that is a contradiction. So, actually it turns out that the z lines in the cross section, they not only change their length, they also become curved. So, actually if we draw more accurate representation of cross section, then the z lines are curved, and it curves in such a fashion that at the edges of the cross section it should be perpendicular, so that there is no shear strain induced on the edges, and likewise there will be no shear stress on the edges. Okay. So, these are actually curved. And we have also found out that epsilon z z is nu times y over r, and can you recall epsilon x x was y over r, and epsilon x x was on the x lines, the longitudinal lines along the axis of the beam, they were also curved. And what was the radius of those circles? It was this big R itself. So, when it is y by r, the radius of circle is big R. Now, for these curves in the cross section, the z lines, so for z lines, which are also curved, then this implies the radius of curvature for z lines is then simply big R by nu, okay, and that comes from this formula over here. The strain has to be y divided by the radius of curvature, and in this case it becomes big R by nu. All right. So, with this I will close the lecture today, and in the next class we will discuss about bending in the beams when it is subjected to transverse force. So, that is no more pure bending. All right. So, thank you.